For more problems and videos like this for linear algebra, you can take a look at Sarai Studies. Link is in the description box below. In this video, I'm going to show you what orthogonal vectors and orthogonal sets are. Now, what does it mean for two vectors to be orthogonal? Well, it just means that they're perpendicular. So if you have a vector u and then you have a vector v, these two vectors are orthogonal. You can graphically see it, because when they intersect, they form a right angle. They're perpendicular to each other. But if I give you two vectors, let's say a and b, and I ask you, hey, are these two vectors orthogonal? Without graphing them, how can you tell? And that is a use case of the inner product, which is the first thing we learned in chapter 6. If the inner product of the two vectors is equal to 0, then we can say that those two vectors are orthogonal. So remember, the inner product is just a times b. So you write this as a, -5, b becomes -2, -3. Then you multiply the first term with the first term, so that's going to be equal to -16. And then you multiply the second term with the second term, and that's going to be equal to +15. And so this gives us -1. And that's not equal to 0, so therefore these two vectors cannot be orthogonal, and graphically that means that the two vectors are not perpendicular. Let's try another one. We're given these two vectors w and z, and we want to know if they are orthogonal. Well, then just find the inner product. So it would be 3, -6, 7, 8, then -9, 6, 17, and -7. You multiply the first number with the first number, that's going to be equal to -27. Then you multiply the second number with the second, so that's going to be -36. Then the third with the third, so that's going to be 17 times 7, that's equal to 119. And then 8 times -7, which is equal to -56. And if you add up all of these numbers, you get 0. So therefore, because the inner product of these two vectors is equal to 0, then we can say that these two vectors are orthogonal. And graphically, that means that they are perpendicular to each other. So I'm going to go ahead and move this down here, and this as well. Now, what are orthogonal sets? Well, remember that sets are just a collection of things, a list of things. It's just that we have these curly brackets around them. And if we're saying that a set is orthogonal, then that must mean that all of the vectors in that set should be orthogonal. They should all be perpendicular to each other, meaning if you pick two different vectors from that set, when you find the inner product, it should be equal to 0. And if you pick another two different, they should be equal to 0. And if you pick another two different, they should be equal to 0. They all should be perpendicular to each other. So let's take a look at this one. Notice how this set just contains the two vectors that we have here. And so the question is this an orthogonal set or not? Well, you would have to check that these two vectors are orthogonal to each other, and we did that already. We found that they're not orthogonal to each other because the inner product of these two vectors was not equal to 0. So therefore, this is not an orthogonal set because it doesn't contain all orthogonal vectors. What about this set? Is this an orthogonal set? Well, it would have to contain all orthogonal vectors, meaning that every vector in this set should be orthogonal. Their inner product should be equal to 0. And we already did that. We checked that the inner product of these is equal to 0. So therefore, because all of the vectors in this set are orthogonal, then we can say, yes, this is an orthogonal set. Now let's try another one. The question remains the same. Is this an orthogonal set or not? Well, an orthogonal set would have to have all orthogonal vectors, meaning that for every two different vectors I pick, so this one and this one, and this one and this one, they all have to have their inner product be equal to 0, because that means that they're all orthogonal. In other words, every single pair of vectors here should be perpendicular to each other. So you would have to check. So I would start with this first vector, so 1, 0, -1, and I would check if it's orthogonal with this one, 1, -4, and 1. So I would multiply the first number with the first number, so that's 1. I'd multiply the second with the second, so that's 0. The third with the third, so that's -1. 1 minus 1 is equal to 0, so that's beautiful. So these two vectors are orthogonal. Okay, keep going, because they all have to be orthogonal with each other. So now let's test this one and this one. Again, the first vector is 1, 0, -1. We're trying to find the inner product of that and 4, 2, 4. First number with the first, that's 4. The second number multiplied by the second, that's 0. And then third number multiplied by the third, that's -4. So 4 minus 4, that's 0. Beautiful. So then these two vectors are also orthogonal. And then we also have to check the last remaining pair, which is these two vectors have to be orthogonal. So that's 1, -4, 1, and 4, 2, 4. You multiply the first by the first, so that's 4. The second by the second, so that's -8. And then the third by the third number, so that's 4. 4 plus 4 is 8, minus 8 is also equal to 0. So because all of the vectors in the set are perpendicular orthogonal to each other, no matter which two different vectors you pick, their inner product is equal to 0, then we can say that this is an orthogonal set. It is literally a set of all orthogonal vectors. So yes, this is an orthogonal set. So if at some point the inner product was not equal to 0, as soon as it's not equal to 0, then you don't have to check the other ones. You can just say, hey, it's not an orthogonal set because not all vectors in the set are orthogonal. And that's it for this video. I'll see you in the next.